Good morning, good afternoon, good evening, everyone, and welcome and thank you for joining us for this GridOS WAMS webinar. My name is Delphine Hafner. I will be the moderator for this session. Today with us, we have Manu Parasha, our Transmission Product Director, and Dan King, our Senior Solution Architect. We are very excited to talk about our GridOS WAMS solution. And this is the first webinar of the GridOS webinar series that we are running for the APAC and India region. We will run a webinar each month until the end of this year. The goal of this session is to help you understand our new GridOS orchestration software. As the grid becomes more complex every day, our customers need new tools. In this webinar series, we will present to you some of the new GridOS applications designed to tackle the new challenges that come with the grid modernization and the energy transition. Today, we will cover GridOS WAMS. Next month will be GridOS forecasting. And in December, it will be the new GridOS Digital Dynamic Line Ratings, DDLR applications. Don't forget to register to join us for those sessions. But every customer that subscribe to the GE Vernova communication will receive an invite for the upcoming sessions. If you don't receive it and you would like to know more about those products, please reach out to your GE sales account manager. Today, we have 1 hour together. Feel free to type your questions in the chat. Ask us anything you want. We will address your questions. And this session is really for you. And with that, we will get started and I will hand over to Manu. Over to you, Manu. Thank you.
Thank you, Delphine. Good morning, good afternoon, good evening, everyone. Welcome. So WAMS, or Wide Area Measurement System, that technology has been around for 20 years. But I'd like to highlight a couple of trends that make this technology more relevant today than it has been in the past. The first is the higher penetration of renewables. We know that with renewables, whether it's wind or solar, we have variability, we have uncertainty, unpredictability. But there are aspects of renewables that affect stability of the grid. Case in point is inertia. The conventional generation that we have has huge rotors that provide mass or inertia that help maintain the stability of the grid. As we retire those conventional generation, thermal, nuclear, hydro, and replace them with renewables, the inertia is decreasing. And what that's resulting in is more variability in frequency, and that is impacting the stability of the grid. So more dynamics on the grid because of that. The other aspect is that most of these renewable generation is inverter-based resources. And these inverter-based resources have sophisticated controls on them. And so the controls are known to create dynamics, and those controls can interact with the grid, destabilizing the grid potentially. We have seen what is called force oscillations on the grid. So all of these physical characteristics of high penetration renewables requires greater visibility into the dynamics, which is what WAMS offers. And furthermore, the agility or the controls to be able to stabilize the grid should there be a need. The other trend that I'm seeing is the acceleration of these sensors. So 5 or 10 years ago, we had dedicated devices called Phasor Measurement Units that needed to be installed, and installing these devices was costly. What's changed is existing relays or fault recorders have the ability to gather this data, WAMS data. And so that's resulted in an explosion of these sensors across the grid. For example, if you look at North America, in a short span of 10 years, the number of devices across North America has grown from a few hundred sensors to thousands of sensors. And therefore, there is a need to be able to scale and consume these large volumes of data. And the suite of applications that we have for WAMs, a dozen or so applications, run them at scale. And that's where the GridOS platform benefits us because it's based on a modern Kubernetes microservice architecture that allows you to scale horizontally and run those applications on scale. Furthermore, it provides the modularity that is needed to reduce the time to value. So, just to uh, talk about the GridOS platform, we are building our WAMS applications on the GridOS platform, and it provides us with a few benefits. The first is a common data fabric, allowing us and our customers to consume not just WAMS data, but combine it with other forms of data, SCADA data, data from our EMS applications, a unified network model so that we can look at WAM's data and use the same nomenclature that we use in our EMS. A grid orchestration engine that allows us to orchestrate across these various applications and a unified UI that allows us to superimpose WAM's data and information on top of information from other EMS applications, such as state estimation, contingency analysis. And one of the things we have heard from our customers is it's not just GE's applications, but they would like to develop their own applications. And that's where the GridOS platform allows us to build, not just deploy our application, but partners, they can build their applications, or customers themselves can also build their applications. Right. So by the end of this year, we will be releasing a GridOS WAMs. And some of the benefits are reduced cost of ownership. In fact, in Brazil, a few years back, we had deployed a microservices Kubernetes WAMS solution. And an example of reducing time, total cost of ownership, there was a defect. And usually regression testing, resolving what would take weeks because of the modularity of this platform, we were able to isolate the microservice, fix the defect, and deploy it in matter of days as opposed to weeks. And so all the new applications that we've developed recently on WAMs, linear state estimation, oscillatory management, effective inertia, dynamic parameter estimation, all of those applications are available on GridOS WAMs. So let's talk about the WAMs applications for the control room. As I said, this high resolution data allows us to look at dynamics or oscillations on the grid. But what we're finding is these inverter-based resources, renewables, are introducing new dynamics that can interact with the grid. Some examples of this. In 2019, in Florida, in the US, there was a generator, and the controls of the generator started creating an oscillation. It turned out that the frequency of this oscillation, quarter hertz, corresponded with the dynamics of the Eastern Interconnection grid. And that caused a resonant phenomenon between this generator and the rest of the grid. And that oscillation propagated across all the way up to Canada. The same year, 2019, in the UK, a wind farm, a lightning strike caused a voltage dip. The controls of the wind farm started creating oscillations and caused the wind farm to shut itself down. And that resulted in a blackout. More recently, in the US again, the Western Interconnection, the western part of the system, a battery storage in Southern California started introducing a quarter hertz oscillation. And again, that coincided with the natural dynamics of the Western Interconnection grid and caused a resonance, and the impact was felt all the way up in British Columbia, Canada, and Alberta. Same year, again in the US, in the Midwest, this time it was a PV farm that started creating sustaining oscillations that lasted for more than 5 hours. So these dynamics and the ability to visualize, analyze these dynamics is important so that we can identify the location of these oscillations and take remedial actions. Let's talk about oscillatory stability management. We've had that application in our portfolio for over a decade. However, what we've done is we've expanded the frequency of the dynamics that we can monitor. So typically, we've looked at the dynamics associated with your conventional synchronous generation, so your thermal plants, your gas plants, and so that's typically in the range of zero point 0.2 hertz to 4 hertz. What we've done is we've expanded the range all the way to 50 or 60 hertz so that we can look at these subsynchronous oscillations as well as oscillations associated with these inverter-based resources. Knowing that the inertia is dropping, on the lower side, we are able to look at governor control kinds of oscillations on the grids as well. What we've also added to our portfolio is what's called source location, oscillation source location, because we know that while oscillations on the grid can propagate, identifying the location that's adding or causing the oscillation is important. It may not be the same location where you're seeing a large oscillation. Being able to pinpoint where there's energy being introduced and oscillations being caused is something that we've added to our oscillatory stability management. What we're showing you here are some of the displays that we have and some of the other applications for the control room. What the first display that you see is islanding, resynchronization, and black start. And it allows you to identify if there's an islanding condition and then visually shows you the different regions that have islanded. So in this example, you can see the portion in the red on the top is one island, and the rest of the blue portion is another island. Another example is about oscillation monitoring. So the display that you see in the center, the trends, it shows you the trends of the oscillation. And on the geospatial, the violation marker pinpoints where the oscillation is coming from. The third is about detecting disturbances and localizing them. And that's another capability we have for the control room. Dan shortly will walk you through a demo of these applications and the visualization for these applications. Now, I talked about renewables and I talked about stability. And the biggest challenge there is, as I said, conventional synchronous generation have these large rotors, and these rotors cannot change their speed instantaneously. And so that buys us precious time when there's a disturbance in the system to minimize the variability of frequency and prevent a potential stability issue. So being able to maintain a certain amount of inertia on the grid is important. This was a challenge for one of our customers in the UK, and we worked with them to use this high fidelity data to be able to monitor the inertia in real time. So that's our effective inertia application. The effective inertia application uses the high fidelity frequency data and the flows data, and through that variability, it's able to measure in real time the inertia on the grid. We use the word effective inertia because it's taking into consideration not just the synchronous generation that's online, but also accounts for any other source that brings inertia to the grid. This could be frequency dependent load. This could be your renewables providing some level of inertia on the system. We also realized that as we have more distributed generation of the grid, the concept that there's only one inertia for the grid is no longer true. We are seeing these pockets of inertia on the system. And that's why we use the word area effective inertia, because we can look at inertia in different regions of the system. So in the case of Great Britain, we have the system divided into 4 different regions, and we are measuring the inertia in each one of the 4 different regions. We're taking that one step further. What we are doing is we are also able to forecast the inertia over the next 24 hours. So here, what we do is we use the WAMS data, but we also use the renewables forecast, the load forecast, the conventional generation forecast, and translate that using AI ML into an inertia forecast in the next 24 hours. That way, um, utilities can plan their dispatch and ensure that they maintain a certain amount of inertia on the system for stability reasons. And so here are some of the examples of the displays that we have for effective inertia, trends of the inertia, the forecasting of the inertia, and we can also go and look at events on the system in the past to validate the inertia using data from the events as well. Another application I'd like to talk to you about is linear state estimator. What it is a purely WAMS-based state estimator. One of the distinctions between WAMS data versus SCADA data, other than the resolution of the data, is that we are directly measuring the state. And therefore, we can use that information to more accurately look at the overall or estimate the overall state of the system. Now, we know that state estimation is one of the fundamental applications in the EMS. We use the results of the state estimator for advanced applications like contingency analysis, dynamic stability analysis, look ahead analysis. And so ensuring that we have a stable and a reliable state estimation solution is important. And that's where our linear state estimator comes in. It gives us end-to-end backup capability to the traditional state estimator. In fact, here in the US, there are regulatory requirements to have a backup to your EMS state estimation, and many of our customers are using WAMS as a means and linear state estimation to meet that specific requirement. And as I said, it is truly an end-to-end backup because in your conventional state estimation, you have your RTUs in the field. The RTUs send data to the EMS and where your state estimator is running. But with WAMS, you have PMUs or relays or fault recorders, so independent devices from your RTUs that are gathering this data. Often the communication is separate from your SCADA data, and the WAMS applications are running on a separate physical server. So it provides that true end-to-end redundancy to your conventional EMS state estimation. One of the questions we get asked often is what level of observability do you need for running a purely WAMS-based linear state estimator? And the rule of thumb is 30% coverage is usually roughly what you need to be able to run a linear state estimator. And that's again because you're directly measuring the state of the grid as opposed to having to estimate the state of the grid. And what I'm showing you here are some of the displays. So for the linear state estimator, we have tabulars, we have trends, and we have one lines. And again, Dan will be doing a demo for you. So before we move on to the engineering applications, Dan, let me hand it over to you for a quick demo of the control room applications.
Okay. Thank you, everybody, for the time. I hope you find these demos very useful. So again, like Delphine had mentioned, please feel free to put any questions you have at any time, and we'd be glad to answer them. So I'm going to start with our real-time applications that Manu had discussed. So I'll be doing the oscillation source detection and location, and the islanding resynchronization islanding detection and resynchronization. I'll also be doing like a high-level demo on our linear state estimator. So what I currently have here, if you're not familiar, is our application that's known as Vision. It acts as a single pane of glass. It has the ability to pull in all of your real-time data information. So we're currently in a WAMS context, but you could also be in a state estimator context, contingency analysis context. If you were running voltage stability analysis or transient stability analysis, you could bring all that data into Vision and visualize that in a geographic layer. You could also combine all these different views and mix and match all this data. We've got the ability to look at voltage halos to see where there's high and low voltage on the system. So very high level situational awareness. But we also additionally have, since it's a geographical map, the ability to pull any kind of geographical information that we wanted to as well. So if we wanted to see weather overlays, radar, lightning strikes, wildfires, earthquakes, etc. So it really grants us that single pane of glass ability to mix and match data from the real world and the data coming from the electrical grid. So what we have across the top, we are in again, we're in the WAMS context. So if you have Phasor Point, some of these displays will be familiar to you, but we have our overview status indicators of WAMS. So starting at the bottom, typically anytime there's a system disturbance, we're going to see this indicator turn red, yellow or red, typically turns red. And then WAMS is looking for islanding conditions, power megavar overloads, oscillatory stability, frequency issues, and then voltage and angle and magnitude issues. We have our oscillatory mode shapes. So we have our different oscillatory mode groups. So starting from 0.04, going all the way up to 4 Hertz in this example. We've got a mode shape data to the right. Also with Vision, it's a great dashboarding tool. So we've got the ability to quickly build graphs and charts of many different types. So these 3 graphs charts here are all frequency, but just in different formats. We've got a frequency gauge chart. We've got a frequency bar chart of readings from across our system. And then we've got our overall frequency of the system, again, being taken from different places, as well as a polar chart. So the first thing I'm going to start out with our oscillatory source location. So let me turn that. I've already predefined a dashboard for that. So typically the oscillations are very small. I've got the damping modes for the first 3 oscillatory modes in a bar chart here at the top. So if if the damping, I believe, is above 20%, essentially we stop measuring it. So if anytime you see the damping drop off here, so when the damping is very high, the oscillations are going, to immediately be squelched out. So we typically don't show very high damping above 20%. But anytime it gets below 20%, we're going to start monitoring what that damping percentage is and then display it accordingly. So I've got a scenario that I'm going to start. So at our Douglas substation, I'm going to put in a forced oscillation on the grid. So we've got our AVR sine modulation. I'm going to pick my Douglas unit 6. I'm going to put in a 1/2 of a Hertz frequency oscillation. I'm just going to make it for a short duration of 45 seconds. And then a 1/4 per unit amplitude. So go ahead and start that oscillation on the grid. You'll see that it starts to show up in our graph here on the right. And then very shortly, our WAMS detects that there's a system disturbance on the system. So WAMS is looking for multiple system disturbances. It looks for line trips and unit trips. So if you have a line trip, you typically see like a very short oscillation, then it almost immediately goes away. For load or generation trip, you'll get a frequency decline or frequency increase that typically persists. And WAMS is not only going to detect those system disturbances, but it's going to pinpoint where those load losses and generation loss are on your electrical grid. So you can see this oscillation is persisting. WAMS has picked up that it's a system disturbance. It's categorizing it that it's oscillatory stability. and it's putting in the oscillatory stability mode. So you can see here our frequency indication is already, our oscillation is already kind of dropped off, but we've got our different oscillatory modes. So this fill of the circle is the amplitude of the oscillation. So the amplitude at Douglas is very small, but very far away, like the ripple on a lake, you're getting large frequency and power oscillations. And then the arrow is the oscillatory mode. So we're seeing a large oscillatory mode deviation. That's telling us that Douglas is the one that's giving the most energy to this oscillation on the grid. I can also change my display mode to show the source locations. And you can see that we're pinpointing the fact that Douglas has the largest fill in this instance. And so Douglas has been identified by WAMS as being the source of this oscillation. So some of the things that you might do as an operator when you see oscillations on your grid and they've been identified in the power plant that's associated, you might determine that there's some kind of a mechanical issue with that plant. So it might be that the power system stabilizer has issues. It might be in a poor operating mode where it's unstable. So one thing you could do is reduce the generation output to get the unit into a more stable operating mode, or worst case scenario, take the unit entirely offline if it's causing oscillations that are persisting and impacting your grid. So what we don't want to have is the oscillations negatively impact with your system protection and cause other devices to trip. And it's also acts as asset health management, where we're getting indication of the performance of our equipment, and we want to be able to protect that equipment and protect the overall electric grid. So my oscillatory oscillation is moved on. So my next demonstration will be on the islanding detection and resynchronization. So what I have in this is our ESCA 60 bus, if you haven't seen this before. So this model is a fictional 60 bus model based in the Pacific Northwest. And what I have here is essentially like a peninsula of generation and load in this transmission ring here. It's connected back to the system there's two transmission lines that connect this ring of load and generation back to the transmission grid. So if I take these two transmission lines out of service, we'll see this smaller island separate from the larger electrical grid. So let me come in. Let's just start with taking out one of the two lines. So WAMS is going to see that we have a oscillation on the grid from the switching of that line. Oh, I'm sorry, I did not. I clicked on the wrong spot. So you see we have a system disturbance. And that transmission line's been taken out of service, so we get some voltage issues because we've weakened this system. We got some frequency problems going on in that potential island. And then when the other transmission line is taken out of service, you'll see that we end up with a very large frequency excursion. So I'm going to change over to my other frequency dashboard. You can see that our two islands have separated. Let me turn on my frequency halos that helps visualize the differences in frequency. So the smaller island is the curve that's shooting up. So we're getting a very high frequency because we've got a lot of generation and little load in this island. And then we've lost that generation source to the bigger island. So our frequency has declined from nominal. So then our large or small island is now kind of rapidly swinging back and forth due to that mismatch of generation and load. I'm going to just adjust the timing scale here just so it's a little easier to visualize. But this is the two islands are going to swing back and forth against each other. So we've got some polar charts that show the smaller island, the frequency is rapidly changing compared to the larger island. So some things that we could do as an operator. So as you saw, whenever the frequency swings low, everything kind of turns blue. So it's hard to tell, which islands are which. So we have a visualization of showing the islands on the system. So it's just as a help to your system operators to show you exactly which substations, so which generators, which load, or in which, island 1 or island 2. And that's going to make sure that they're acting on the correct generators or loads to get the frequencies balanced between these two. We also have the ability to easily, if we wanted to turn that off for a second, if we wanted to compare like a frequency node pair or a phase angle node pair, can easily create those on the fly. It's going to tell me that I've got a phase angle difference here. You can see it's rapidly changing between those two. So we want to get our frequencies within limits. We can set limits, high and low limits on this frequency indication, but this is just another tool for your system operators to use to ensure that you've got the correct voltage in both islands across that open corridor, and that your frequencies are matched up across that open corridor before you ever try to close this path back in. So that's going to ensure that you don't end up with a large power inrush that would potentially collapse that smaller island. Pause there for a second in case there's any questions before I move on to the linear state estimator.
There is one question done in the chat. Does it have to be geographic displays, or can it be on schematic diagrams?
I believe I have, I don't know if I have it in this display, but in WAMS, well, I'll let Manu maybe talk to that, but you could set up like a block diagram of your system.
Yeah, Dan, you can have the choice of geographic or schematic diagrams. Both are possible.
Okay,
thank you. Thank you very much.
And then I also
no more questions for now.
Wanted to touch quickly. Our WAM system also does communicate over our proprietary internal ISD link. So we have the ability to bring all of our WAMS alarms into our EMS system. We can monitor those same oscillatory modes, just like we're monitoring them in Vision. We can pull that into a EMS context. We can do additional things. If you've got a specific corridor that you're worried about power angles, you can monitor that. And then you can also monitor post-contingent angle differences on your in EMS coming from WAM. So, but right now I'm in an islanding condition, so it's giving it's going to give some poor results. But it is also not all, we're able to represent this geographically and situationally, but we're also be able to bring that into our EMS applications as well. So I just wanted to quickly point that out. So, our linear state estimator, Manu had already talked about. Essentially, it's I'm located in North America in the Midwest here, but we have requirements per NERC that we have to run a real-time assessment once every 30 minutes. So you always have to be aware of what's going on the grid at a minimum of at least once every 30 minutes. Obviously, you'd be doing it way more often than that, but that's the bare minimum that our regulatory body expects. So what you traditionally would use in that case is a EMS-based state estimator, which runs very routinely, runs very well, except for when you have data quality issues. So if you have PMUs in the field, or if you have a front-end processor fail, then you lose a large percentage of your PMUs on the system or the visibility into your substations, your state estimator will fail. So the linear state estimator acts as a backup to your traditional state estimator. It's using a different data source. Manu showed that very well in that slide. So you've got your traditional RTUs in the field bringing back data to your traditional state estimator, and then you've got PMUs feeding your linear state estimator. And then there's also some hybrid examples where with those two can coincide with each other, but in this case, we're just running a linear state estimator just purely off of PMU data, completely by itself. So right now, this system model basically splits the footprint into two islands at random different times. So we've gone from one island now to two. But we just have some high-level KPIs across the top. We're showing off the total number of observable buses and then the overall total buses. So any bus that's not observable is being estimated, right? We've got a count of our measured versus estimated voltages and our measured versus estimated currents on the system. As our island splits into 2 islands, we're going to keep track of the observable buses in each island and the voltage and current measurements, make sure that our air processing is good, and then our data quality across the system. So also the solution cost index, so that's just a measurement of the effort that the linear state estimator is going through in order to get a solution. The linear state estimator is running at the sub-second rate, pretty much at the same rate that the incoming data is coming at. So it's very fast and robust. And like Manu had already mentioned, it's a linear state estimator because it's already measuring the actual state of the grid. It's measuring the magnitude and angles on the grid. And so it reduces the whole state estimated solution down to just a linear algebraic problem. And so that's why we're able to solve it at such a rapid speed. So some additional information that you'd want to see as an operator or as somebody who's using a linear state estimator, you would want to see the violations on the system. So we just have 2 violations simulated here. So at Brighton, we've got a transmission line that's exceeding the amperage limit on its load shed rating. So we're at 135% of the 250 amp rating on this transmission line. The corridor is a tie line, so it's a transmission line that ties to your neighboring system. We've set a megavar limit, so it's in an abnormal state. So that megavar loading on that transmission line is very high and abnormal, so it's something we'd want to bring to the operator's attention. We want to look at the observability on the system. So at Brighton here, we've got some measured currents on the system on our transmission lines. We're also going to look at the measured node voltages on our Brighton substation. And then if there's a couple, we've got some transformers. So on all of our transformers, we're estimating the currents through the transformers in this demo system. I wanted to look at another substation. So our Park Hill is a fairly large substation. I can see we've got some estimated currents on the system between our 345 and 138 bus voltages. I want to look at the voltages here. We've got some measurements on both the 345 and 138, and then our transmission lines leaving the Park Hill substation. The show corridors, that's essentially is just a summary display that's showing all the different tie lines. So again, the tie lines that connect your electrical grid to your neighbor's grid. And turn those back off. And then the trends. So we can trend any value that we want in the system. So if we wanted to look at the Brighton voltage, we want to make sure that our estimated values are in line with our measurements. So I can turn these different layers off and on. As I hover over them, I'm going to get a tooltip that's going to tell me the timestamp that this was calculated and what my estimated versus my measurement are. So I can easily tell if, my voltage magnitude and voltage angles are in alignment with each other. I can look at, again, trending the different, I believe are from the islanding conditions that are routinely going on. So, and one other thing that I mentioned, like Manu had mentioned, this is a state estimator. So it's capturing the state of the grid, but it's also doing estimation. So it's basically cleaning up the data and making corrections. So if there's any kind of incoming incorrect data, it's going to correct for that and solve to a appropriate solution. So I just wanted to take an example here. So if I go to, let's go to Chenot, this T540 PMU, I can go in and edit that. What I'm going to do is put in an angle adjustment on that. Let's say if I put an angle adjustment of 8 degrees and save that. So I was at Chenot and my T540. So you'll see here that that I've got a my angle offset. So I put in an 8-degree offset, but my estimate is still in the appropriate alignment. So when they were in alignment with each other, there was no offset. They were solving directly on top of each other. So our estimates and our measurements are directly in line. And when I put in that 8-degree offset, which happened here at this moment in time, you can see that the measurement is still coming in with an 8-degree differential, but the estimate is correcting for that and putting in the correct value. So it's solving around the incorrect poor data that's coming from the PMU out in the field. And that was
Dan, maybe can we pause here? There's a few questions in the chat, if that's okay.
Yeah.
Okay, first question is for the linear state estimator. Do we have to create another model, or can we use the same model using the normal state estimator?
I believe you can use the same model as the linear state estimator. And I'll verify that with Manu.
That's right, Dan. You can use the very same model. We can take it from the NetMom model, or we can use a SIM format as well.
Right.
Okay, perfect. That was the next question. Can the linear state estimator solution be exported in SIM16 format? SIM16.
Yes, so we can import the model in SIM16, Delphine, but to export the LSE solution in SIM16, that's part of our roadmap.
Okay, thank you. And then the last question was, although you have the voltage angles measured, but not all the measurements are accurate, CT and VT saturations and time delays may causing some errors. Does LSE handle these errors?
Sure, I can take that one. Yes, it can handle this. In fact, that's one of the benefits of LSE, that it can correct for either CT, PT calibration issues or time delays, because what you're doing here is you're using the data and ensuring that it satisfies the laws of physics with the model, right? And an example was what Dan showed, where he entered an offset and LSE was able to correct. So in addition to giving you the state of the system, it can actually correct for issues that you have with the measurements themselves.
Can the LSE solution be exported in NetMom format?
Currently, it cannot be, Delphine. Again, something that's part of our roadmap.
Okay, thank you.
Right. So on the engineering applications, so these are applications where we can use historical WAMS data for back-end engineering functions, things like post-event analysis, etc. One of the applications I'd like to specifically talk about is validating and calibrating dynamic models. Because we can observe the dynamics on the grid with this data, it's valuable feedback that we can use to firstly identify if the models are not correct, and if they're not correct, use it to then calibrate the parameters of the model. And what I'm showing here are two examples. The first is a rather old example, but nonetheless, it shows the point. So this was the US Western Interconnection 1996 blackout, where the Western Interconnection separated into 4 different regions. Now you're seeing 2 trends here. The trend on the top was what the dynamic models were predicting, the blue trend. The trend below is what was actually measured by fault recorders. And what you can see is a real mismatch here, because the blue trend is showing a stable system, while the red trends are showing growing oscillations, which resulted in the system, again, separating into 4 different regions. So again, the need for having these models accurate is important. More recent, if we look at a 2020 case of the Western Interconnection, And in this case, we are focusing on the renewables, so the inverter-based resources. The top pie chart shows the percentage of wind plant models that are inaccurate. The top half of the pie chart, 50% were, so everything above the red line were models that were either incorrect, obsolete, or were not using the right model. And of the remaining 50%, the bottom half and the blue portion, a majority of them were using default values. So weren't again reflecting the actual physical asset that was there, uh, wasn't being represented. The same thing with the solar PV models. What was found was 93% of the PV models were inaccurate. So again, the need for being able to calibrate these models, and this is where WAMS comes in, because as I said, you can observe the dynamics, and it becomes a non-invasive way of calibrating the models, because the conventional way of calibrating models is usually taking the plant offline and running staging tests, which means downtime. Here, using events that have happened on the grid, you can take that data from the events and use it to calibrate the dynamic models. So this is part of our offline application, a non-invasive way of calibrating dynamic models. And I've got a short video here that walks you through the process. Okay, so as I said, the first step in the process is validating, do I have the right dynamic model? And so in this application, what you're seeing at the bottom are frequency and voltage trends during the during an event. And on the top, you're seeing the megawatts and the megawatts. And what we're doing behind the scenes is we're taking the frequency and voltage as the independent parameters, and we are driving the model and looking at the response of the model in megawatts and megawatts, and comparing the response with what was measured from the WAMS system, the two traces on the top. So as you can see, if you look at the blue traces, that was what was measured, and the white dotted trace is what the simulated dynamic model is telling us after we have fed it with the independent variables, the frequency and the voltage. That's what we call a force simulation. Clearly a disconnect because those two traces don't match. So then we go on to the next step. And what we're doing here is we are doing a sensitivity analysis where we are looking at what parameters are observable. And what it does is it comes back and it tells you the set of parameters that it thinks we can calibrate, the ones that are checked. There are minimum and maximum ranges for these parameters as it goes through the optimization to calibrate it. And we have different elements of the dynamic model. So we have the power system stabilizer, we've got the governor model, etc. And then when you click on the calibrate button, what it does is it then goes onto the calibration. As I said, this is an optimization algorithm. And what it's doing is it's tuning the parameters such that the error between what was measured versus what is simulated agrees. And so it's going through iterations. And as you can see, with every iteration, the residual or the error is dropping. And it's coming up with the results of the calibration process. And once where the error tapers off, and if you look at the results on the top, you can see there's a new dotted white line, which is the calibrated simulation. And that calibrated simulation agrees much more closely than what was measured. So again, an application where we're using WAMS, in this case, for offline analysis, and using to improve your dynamic models. Okay, going back to my slides, I'm going to talk about wide area control. As I said, WAMS gives us the agility for fast response should there be an issue with the stability of the grid. And the example I'm going to use here is the Great Britain example, because as you have more renewables on the system, the frequency can drop much more faster when there's an event than when you have conventional synchronous machines with the inertia on the system. And so with WAMS, you can use fast acting resources such as batteries or flywheels to help bring the frequency back. So that's one of the advantages. But the other aspect of this is location matters. And location matters because, as I said, inertia is no longer one for a system which has high penetration of renewables. We have these pockets of inertia in the system. So acting at the right location becomes it becomes important. In this example, which is the Great Britain system, what I'm illustrating here is, so there was an interconnector loss, which caused the frequency to drop. Now, in this case, we used generation pickup up in the north to bring frequency back to normal and balance the supply and demand. But because we did it in the north, it caused additive stress across the system because the loss was down in the south. And so the angle separation between the north and the south increased even though we were restoring frequency. And as a result, the system separated. And so with our WAMS solution, we have something called fast locational balancing, which can use the fast resources such as batteries, etc., but also use them at the right location such that you're restoring frequency while ensuring that you're not adding additive stress to the grid. You're maintaining the stability of the grid. And so with our effective inertia solution and with our locational fast balancing solution, we've got an end-to-end offering for managing low inertia grids with higher penetration of renewables. As I said, the inertia monitoring uses WAMS data to measure inertia in each one of the regions, uses AI/ML to forecast, and then the WAMS controller allows us to then implement the control scheme, locational fast balancing, to help in the event that there's a disturbance to stabilize the grid using fast acting resources where they're available. And so on the wide area control, we have two different platforms. We have a lightweight phasor controller platform that's a smaller form factor and can handle situations where you have small number of PMUs. But we also have a large form factor solution, which is our GE Power Gateway or GPG solution. It can handle far more PMUs and has more advanced control capabilities beyond WAMS control applications. Both solutions are part of our wide area control offering. Right. So in conclusion, I walked you through the different application that we have in the WAMS portfolio. As I said, the WAMS applications we spoke about are on our GridOS platform. And at the same time, we are working at transforming or moving our conventional EMS applications, our generation applications and transmission applications on the GridOS platform. And we intend to have a first version of our GridOS EMS by the end of 2024. And so by having the WAMS applications on GridOS, along with our transmission generation analytics applications, we can actually have an ecosystem of integrating these different applications. So as an example, having linear state estimator not only be a backup to your traditional state estimator, but using linear state estimator as a mechanism to firstly clean your WAMS data and then feed the results of the linear state estimator to your traditional state estimator is possible because these applications, again, coexist within the GridOS platform. With that, I'll hand it over to you, Delphine, and open it up for questions.
Thank you. Thank you very much, Manu. We've got a few questions for you in the chat. I'll start with the first one. That's regarding the model validation and calibration. Since the parameters are estimated from limited number of events, can we believe that the parameters can be accurate for every event?
Delphine, that's an excellent question. And what we have done is we allowed the model validation calibration done across a set of events. So if you have a history of events, we found that using it on one event or a couple of events isn't adequate, as was pointed out in the question. So we have done it, implemented the algorithm so that we can take a library of events and optimize across that library of events, which improves our confidence in the results of the model validation and calibration.
The next question that was to find the parameter in model validation, can we use many events to tune the parameters? So the answer is yes. I think there's no more questions, and we are at the top of the hour. So we will say thank you to all of you for joining us, and thank you to our presenters today. We really hope you found that session useful, and we are all looking forward to seeing you again for the next event next month. Thank you, and bye for now.